Hey guys, welcome back. Today, RLC parallel three-phase circuits. All right guys, and the good news is you already know how to do this. So the only thing I have to show you is that you do indeed know how to do this. I know, tons of questions, okay, A through U, terrible. It'll be all right guys. I'll show you that it's not that bad. First thing I want you to notice is that there is a alternator up here, so no transformer for now, okay? And don't sweat it. That's a Y-connected alternator, and it's feeding these three loads with 600 volts, okay? And so it'd be like the same as having a secondary of a transformer here. That's connected Y. Let's do these one at a time and not sweat it here. E-line load 1, guys. Here's load 1. It's a resistive load, happens to be connected delta. Look, it's getting a line voltage of 600 volts. So this is simply 600 volts, okay? Because if that line voltage coming out of this thing is 600 volts, then the line voltage feeding all these loads is 600 volts, okay? E phase load 1, that's delta, with delta E line is equal to E phase. I phase load 1, we've got 600 volts from here to here, guys, and it's dropping over this 75 ohm resistor. So that's going to be Ohm's law, 600 divided by 75, okay? 600 divided by 75. Looks like it's 8 amps. I line load 1. This is delta. I've got 8 amps here and 8 amps here. That means the line current feeding that is going to be 8 times root 3. So this is going to be 8 times root 3. And I'll just calculate that here for a sec. 13.86. Okay, now, while we're here, guys, we'll talk about this for a second. That is not this line current right here, okay, because that line current is feeding this load and this load and this load. That line current actually would be right here, okay, there, there, and there. That little bit would be 13.86 and then splitting 8 amps in each branch, okay? But let's do load 2 and load 3. If you want to, you can pause the video here and try doing load 2 and load 3 up to M here and then come back. And I'm going to do it right now, exactly the same as I did load 1. Okay, so this is going to be the line voltage feeding load 2. It's a Y-connected, looks like a bunch of inductors. It's going to be 600 volts. Okay, E phase load 2 is going to be 600 divided by root 3, okay, because it's Y. 600 divided by root 3. 346.4 volts. I phase load 2. I've got 346.4 driving across 51 ohms. It's just Ohm's law. Okay, looks like it's 6.79 amps. I line load 2, which should be this little line current right here, be there, be there. It's Y, so it's 6.79 amps. Load 3, done exactly the same way. Line current feeding that load, 600 volts. Okay, phase current, it's delta, so it's 600 volts. Current in there is going to be the 600 dropping across that 70 ohms. Okay, so this is going to be 600 divided by 70. 8.571 amps. Okay, and now we're at I line load 3. That's going to be this little line current right here feeding that. It's going to be 8 there and 8 there, so it's going to be times root 3. 14.85. Whoops. Okay, guys. Now, here's what we've done so far. Okay, we calculated the line current feeding the first load. We've calculated the line current feeding the second load. And we've calculated the line current feeding the third load. Now, the next thing it asks for here is I-line alternator. In other words, what's the current leaving this alternator? And that's actually I total for the circuit, guys. It's going to feed this load, and that load. So it's going to be the sum of the line currents, guys. But you must add them as phasors. All right, guys, because those are out of phase. In fact, load 1 is resistive, so that's IR. So if I drew it right here, where should I draw it? Right here. That's 13.86, and I must add up line currents, by the way. Can't add up phase currents because that wouldn't be the complete picture. Okay, so there's IR. This one here, the 6.79, that's IXL. Okay, it's going to lag by 90, right? So it's going to be straight down here. IXL, and that's going to be the 6.79 amps, right? And load 3 is a capacitor, so it's going to be IXC, right? So it's going to go like this. It's going to be 14.85 amps. And this here would be IX, right, guys? And I can calculate that. It's going to be 14.85 minus 6.79, so minus 6.79. Looks like it's 8.056 amps right there. And the sum of the three, guys, is going to be the total circuit current. In other words, I total. This is going to be I line alternator. Okay, and obviously I can calculate it using Pythagorean theorem, which is what I'm going to do right now. Okay, so it's this squared plus this squared square root. So I'm just going to hit squared plus 13.86 squared equals root equals, looks like the total circuit current or the line current coming out of the alternator is 16.03 amps. Okay, and I would measure that right here, 16.03 amps. Okay, and it would be feeding these three line currents right here. Now, that is the answer for this, 16.03. Okay, one thing at a time here. Now, next question, I phase alternator. It's asking about the current in a phase. Well, this alternator is Y, so it's going to be the same, 16.03 amps. If it happened to be delta, then I'd have to calculate it with a root 3, right? But it's not, it's Y. Now, lucky for you guys, all my alternators are Y for some unknown reason. Okay, I don't know, I could have put a delta, but I never do. So all your homework is going to have Y connected alternators. So the line current and the phase current coming out of the alternator is going to be the same. All right, guys? Now, let's take a look at this next one, which is the true power in the circuit. Now, the true power in the circuit is any power in the circuit due to the resistance of the circuit. And you'll notice that there's only one of these loads that's resistive, and that's this one. What that means is if I can figure out the VA of this first load, then I will have, you know, the true power for the entire load, because this VA here will be equal to the power here, right? Because this has a power factor of 1. And so I'm just going to use a VA formula for calculating it, but I'm going to use, you know, the VA formula just on load 1. So the power here is going to be E line load 1 times I line load 1 times root 3. In other words, if I take, you know, E line load 1 and I line load 1 and multiply it by root 3, I will have the power for the entire circuit. So this here is going to represent the power. And so it's going to be 600, got to use line values if I'm going to use root 3, 13.86, okay, times root 3. What I'm doing is calculating the VA here, and the VA here is the power for the whole circuit. Okay, guys? So I'm going to calculate that for a second here. 600 times 13.86 times root 3. It's 14,404 watts. Okay, now for the VARS XL and the VARS XC, I'm going to do exactly the same thing. For VARS XL, I'm going to calculate the VA of the inductive load. In other words, these two are going to be VARS XL. And in fact, these two, okay, you know, this one, L, those are going to be VARS XC. because it's the VA of the capacitors, the VA of the inductors, the VA of the resistors, okay? So I'm going to calculate these two exactly the same way. For the VARS XL, I'm going to take the line voltage for the inductors times the line current for the inductors times root 3. 600 times 6.79 times root 3 equals 7056 VARs. Okay? And same with this one. I'm going to take the line voltage feeding the capacitors, 600, times the line current of the capacitors, 14.85, times root 3, because it's a capacitor bank of a three-phase capacitor bank. Okay, it is 15,433 VARs. Okay, guys? Now, I have the VA of this entire circuit to calculate it. Now, there's a bunch of ways to do this, and I'm going to show you the Vanandel way. All right, guys? Because there's other ways that are legitimate and they work, but there's, easy way and hard ways to calculate the VA of this entire circuit. The hard way would be to draw a phasor diagram with those, three powers, because we know the VA is the sum of all the powers in the circuit. So, I could have 14,404 and then 7,056 and then 15,433 and calculate the VA, which will be the sum of the three, and that would work. But the way I'm going to calculate VA, guys, is I'm going to take I line for the whole circuit, E line for the whole circuit, multiply it by I line for the whole circuit, and then multiply it by root 3. Because the VA of every circuit is E line, I line, root 3. Okay, so E line is 600. I line is 16.03. I'm basically using total values now. Total voltage, total current, times root 3 to get the total VA. 600 times 16.03 comes to 16,659. Okay, guys? Now, a couple of little things left to calculate. One is the power factor. Well, I could calculate this angle and hit cos. But power factor is P over VA, so that's how I'm going to do it. It's the total power in the circuit over the VA. So it's going to be okay, 14,404 over 16,659. Let's try that. 14,404 divided by 16,659. Looks like it's 0.865. Okay, and guys, there's a lot of ways to do these things now. There's a lot of correct ways to do it. So do it however you like. Okay, because now it's asking for the phase angle. I could have calculated the phase angle first and hit cos. Then I'd have both of those. Whatever you want. Okay, guys. So I'm just going to hit inverse cos. Shift cos to the power factor. Okay, guys. 30 degrees. Okay, guys, and that'll work. And then does the circuit lead or lag? Well, I have to identify the phasor current. It is leading. Okay, according to my phasor diagram here. So, terrible, I know. Come back and we'll try the next one on the next page. Okay, guys?